Okay, can everybody hear me in the back? Good. So today I'm going to talk about paradigms of probabilistic programming. Before I dive into the technical content, though, just a few words of motivation. So we might have forgotten, but 10 years ago, I actually think there was the sort of early signs of peak excitement about machine learning and big data. So, for example, the editor-in-chief of Wired wrote an article saying that the data deluge was going to make the scientific method itself obsolete. And, about 9 years later, we saw success stories like AlphaGo Zero, which I think validate one important aspect of the machine learning paradigm, but I think also highlight some of its limitations. And most of my talk today is going to be about its limitations and ways to remedy them by bringing in ideas from programming languages. But I think it's kind of worth taking a look at the success stories first to contextualize. So AlphaGo Zero is a Go-playing AI system that is trained based on synthetic data generated from self-play. And it takes about 5 million games of Go to generate enough data for the neural net that estimates the value function in AlphaGo Zero to get good enough that the overall system exceeds top human performance. But I think it's helpful to position Go on a spectrum, which will let us understand the range of AI applications that are emerging and why we might expect, just based on these successes, that a new programming model is needed. So Go is a game which is easy to write a simulator for in software. The rules have been fixed for over 2 millennia. Also, in each Go game, it's easy to determine the winner and the loser. That's an objective feature baked into the game design. But as you move away from Go and towards problems faced by, let's say, ride-hailing providers like Uber, one of the companies which has been helping to create the field of probabilistic programming, you find problems where it's actually impossible to make accurate simulators of the world. Partly because roads and cities vary widely from day to day, in some cases hour to hour. And even if you had simulators, the machine learning paradigm struggles in another way, which is that it's hard to tell what a good simulation is, as drivers and riders have complex and often inherently conflicting objectives. And as you move from problems faced by companies like Uber to, let's say, problems on the frontier of experimental science and translational research in cancer, you find the data is even sparser and more difficult to simulate, because within one tumor, within one patient, every cancer cell may be different. And treatments require making life and death trade-offs for patients using factors that are where the fundamental science and medicine is very poorly understood. Okay, so sort of the largest framing for this talk is that the probabilistic programming community has been developing programming models that are, at least in principle, applicable to AI problems across this range of applications. And they build importantly on the successes of machine learning, but I think go beyond it in interesting ways. So in this talk, my goal is to give you a sense of some paradigms of probabilistic programming, including maybe the most popular version of probabilistic programming in terms of language adoption, but also some emerging paradigms, and in particular, probabilistic programs where the inference algorithms are programmable, not just black box, and probabilistic programming paradigms where the probabilistic program isn't actually written by a person, but is synthesized by a synthesis algorithm. So you can apply this probabilistic programming paradigm to scenarios where you don't have a probabilistic program, but you do have data. Okay, so what's probabilistic programming? If you had to boil down the field to 2 technical ideas and put a programming language's spin on it, you might say this. The first idea in probabilistic programming is that we can take probabilistic models, which are objects we normally are taught to think of mathematically, and represent them using executable code, specifically code that makes stochastic choices. And the second technical idea is that we can take operations on probabilistic models and represent them as metaprograms. That is code that takes the code representing a model and analyzes it or transforms it or produces new code maybe representing a model. So example operations include finding probable values for the variables in a probabilistic model. That's sometimes called inference. Or finding the parameters or maybe even the structure of models given data. Or making predictions for new data given a model. Or estimating the amount of information between groups of variables in a model. And if we can do this, I mean, what we're left with is the ability to factorize code for modeling and inference and these other operations, which provides a kind of automation that's analogous to what systems like TensorFlow and Torch have provided for mainstream deep learning methods, but for a much, much broader class of models and operations. That extends on that AI programming application spectrum, past the setting where traditional deep learning readily applies. Okay, so let me give an example. So here are 4 data sets. This is just a warm-up example. And I'd like you guys to sketch in the air the curve that you think goes with each data set. So for the first data set, what's the curve? Okay, great. What about the second data set? Great. Most people went like this. Okay, one person went like this. Do you really believe that? That's the curve? No, right. And then they shook their head. Right, okay. So many of us had the intuition that these 2 data points are outliers, right? Or for this curve, for this data set, what's the curve? Okay, great. And for this one? Okay, good. So let's see if we can make a probabilistic program that emulates those judgment calls. So if we were doing this without probabilistic programming, we might describe mathematical assumptions that are sufficient to solve this problem, at least in principle, using either statistician's notation or a probabilistic graphical model. The basic idea is we define random variables for the degree of some polynomial, let's say, which is going to be assumed to describe the data. We're going to have distributional assumptions about the coefficients, and then we're going to have variables that indicate whether or not each data point is an outlier. You can notate that in various ways. So here is a probabilistic program written in an early version of a language called Gen, which implements that probabilistic model. I'm just going to talk through it briefly. So here I'm showing the source code, and here I'm showing a data structure called an execution trace, which shows an assignment of a bunch of stochastic choices that are made in the execution of this code to one set of values. So what this code does at a high level is it generates a degree of a polynomial from some categorical distribution, loops over a vector generating random parameters. Then, for each x coordinate, this whole thing takes as input a vector of input x values, it checks what the degree is and evaluates the polynomial at that input point, then generates a choice representing whether or not this data point is an outlier, uses that to select a noise value, and then generates the output from the appropriate Gaussian distribution. And over here, I'm showing one execution where each of those stochastic choices is given a name, and here you're seeing the values associated with those choices. So conceptually, this is that first idea in probabilistic programming. We're taking a model and we're representing it as code, which makes a stochastic choice for each variable. And the space of possible executions of this code, that is the space of possible traces, is the domain over which the probabilistic model is defined. And in the course of this talk, we'll see examples of probabilistic programs that have domains like this, but also probabilistic programs that generate random scene data structures that are fed to graphics engines, and probabilistic programs that generate probabilistic program source code so that we can learn probabilistic programs from data. Sometimes that's the whole talk. Okay? So what's inference? Inference says I have a program and I have some data which I'm going to represent as one of these trace objects where only some fraction of it is filled in. And I'm going to be looking for executions of the program that are compatible with that trace. So maybe there's a prior distribution on traces that's induced by the program. And conceptually, we can associate the program with a posterior and a set of observations with a posterior distribution on traces, which is the prior distribution but pinned down to the observed data at all the addresses in the execution where values were provided. And the goal of inference is to somehow approximate this thing, so to come up with a program representing an approximation to the posterior distribution on traces. So what does it look like to have one of those inference approximations? Well, for example, maybe I make a trace, put in some values, if I view those xy pairs on a plot, it looks like this. So maybe if we saw this data, we'd expect that there'd be a line that should go with it. And so if we feed this as input to this query operation that implements inference, here I'm showing two sampled traces, which are both high probability under the posterior distribution. So they reconcile that program with the data. I could also make a trace that just has a single data point. And now if I run the query operation, I get executions that have widely varying degrees, right? Because with just one data point, the curve could be basically any. Except, well, not anything. It has to be any curve that kind of goes near the point that was provided. Okay, so if we just take that idea and we apply it to this application, it turns out we get results that look kind of like this. So they're a bit blurry. They don't actually do a great job, not nearly as sharp as our own visual intuition. So we can fix that by enlarging the model to include some additional random variables. In particular, we can add in random variables that take the constants in the previous model, namely how likely is a data point to be an outlier and how noisy is the curve, and make those random choices as well that have to be inferred from the data. So if you were to do that in math notation, that's what I'm showing on this slide. To do it in code, you just take the old code and you insert a few lines right in the middle, these three lines here. And now the space of traces is larger and includes those hyperparameters of the model. And if you just visualize random executions, what you see is the old program generates executions that are all pretty noisy and blurry, but the new one generates some executions that are blurry and some that actually kind of closely match curves. And that's the basic intuition for what was going wrong before and what we can fix now. And if we apply the new program to the four data sets, we get posterior distributions on curves that very sharply match our intuition. So here the data fits the line and all the posterior traces or curves closely agree. Or here the system is very confident that there's a line and these two data points are outliers. That's why they're colored in red. But here it's interesting. The system's very confident that this is an outlier, but it thinks this is probably a line, but it might be a cubic. So that's the basics of probabilistic programming. And if you learn a probabilistic programming language like Stan, let's say, you'll learn about that model, but that programming model, but applied to a class of probabilistic models, roughly speaking, hierarchical Bayesian models that are popular, defined over only continuous latent variables, that are very popular in applied statistics. But in fact, probabilistic modeling and inference is applied in many fields. So we could solve statistical problems, kind of like the ones I was alluding to, right? And the problem I showed wasn't really statistics, because there was very sparse data and these ambiguous outliers, right? But we could look at more traditional statistical problems where you're just trying to estimate numerical effect sizes. And that's one domain where you could do modeling and inference, but there are other domains, like in robotics, let's say, in the state estimation systems that are part of an autonomous vehicle, where you have probabilistic models that are defined over tracks of the vehicle and people in the environment. Or in machine learning systems where you have models defined over neural net parameters. And in these different domains, it's not just the models that are different, the inference algorithms tend to be quite different. The way you look for probable executions. So maybe in statistics, people use Markov chain Monte Carlo techniques to try to quantify the uncertainty very precisely. But in a robotics application, you know that sort of from frame to frame in your data stream, the distributions only change a little bit. Interesting. Well, that's Google Voice. So here maybe one would want to use a particle filtering technique. Or in a machine learning application, one might want to search for the best parameters using something like stochastic gradient descent. So somehow, if we want probabilistic programming to be applicable across the range of problems where modeling and inference can be applied, we need to get out of the mode of just specifying a model and hoping to push a button and have inference just work. So the standard paradigm of probabilistic programming is one where you use code to define a model, and there's some data and a query, and then the system somehow pops out an answer. And this is a model that I think maybe was first popularized in the programming language community by some work in 2008 by my colleague Noah Goodman and myself. But I've really honestly been skeptical of this model for a long time because, as we know from programming languages, this kind of purely declarative programming model can easily encounter enormous difficulties scaling across programmers and scaling to harder instances of a given application. So how can we move beyond this sort of magic black box inference engine inside the probabilistic programming system? We don't expect that there's going to be one inference algorithm that is suitable for all applications, right? Different applications have different functional requirements. They need to get some different kinds of things right. They can tolerate different kinds of errors. So somehow we need to extend the paradigm to formalize the space not just of models, but of algorithms acting on models. So in PLDI this past year, we introduced this notion of inference metaprogramming, which extends the model so that your probabilistic program includes your model as code, but it also includes an inference metaprogram, which is a different kind of code that controls how the probabilistic programming system explores the space of traces of this model and lets you implement a broad range of inference algorithms. So this approach has been used to implement a bunch of systems, including a system for discovering structure in time series data. I'll show more about that example in a minute. But sort of the bottom line is that, for solving time series forecasting problems like the one shown here, if you have inference metaprogramming, you can implement these sorts of applications much more concisely than you can with traditional programming constructs. And that's also true for other kind of automatic data modeling and machine-assisted data science applications, including a couple that have been the basis of commercial systems that have come out of my lab over the last several years. So for example, this is an inference metaprogram that implements the backend for BaseDB, which is an open source probabilistic programming platform that has built-in automatic model discovery. And it's, again, only about 50 lines of code to implement the core algorithm, but the first C++ prototype was 4,000 lines, roughly, of C++. Now, certainly, inference metaprogramming in a probabilistic programming language like the one I'm showing here is a lot slower today, but it's slower because we haven't yet done the serious compiler engineering that's necessary to reduce the constant factor overhead. There's no fundamental reason why it's slower other than all the fundamental reasons why higher level languages that have relatively immature compilers are shockingly slow. So let me just show you what the model is so you get the concept of inference metaprogramming. So here, in this box, I'm going to show code. And here I'm going to show a visualization of the state of the interpreter, which is often going to be just one execution trace of that code, and sometimes I'm going to show many execution traces overlaid in this box. And then down here, I'm going to show a graphical depiction of the trace itself. So this line of code is saying I'm going to define a variable x and give it a Gaussian distribution, draw it from a Gaussian distribution with mean 0, standard deviation 1. And I'm going to label it with two names. I'm going to say it's a latent variable and it's called x. So you can visualize that scenario here, right? X is on the x-axis, the value we've sampled is right here, and this is just a reminder that it came from this distribution. And over here I'm showing the value of x along with the name latents x. And that's going to be important because I'm going to need to write inference algorithms that take specific variables and do things to them. Okay, so now I can add a new variable y, which also has a Gaussian prior. So now I can visualize the space of traces of this program like this. There's a Gaussian distribution, the 0 mean, and this little white x represents the particular execution we're on, where here I'm showing y in addition to x. Now I can add in some data. So I might say observe that a Gaussian whose mean is the sum of x and y happen to take on the value 3. So now the distribution rotates and shifts, and here I'm adding on this other choice, which I'm forcing to the value 3. So now we've defined a model and a query. Implicitly, the query is, what are x and y, given that a noisy version of their sum is 3. So here's a fragment of an inference metaprogram that's going to let us start to solve this problem using gradient descent. And so one way I want to solve this problem is just do gradient steps on this probability distribution to try to find the most likely value. Well, here I'm going to say, do gradient descent on a subproblem of this problem that you generate by taking all of the latent variables and treating them as a block and trying to update them with gradient descent as a block. So that's what this line translates to. I'm going to use a step size of 0.01. So the target of that inference metaprogramming instruction is x and y together. That's what this target says. And if I change those two values, the result has to be checked against this value 3, which is called the absorbing set. Right? It's the part of the execution that we're trying to hold fixed. We want to change x and y, we have to figure out how compatible is that with the other parts of the execution. The minimal subproblem is both the target set and the absorbing set, roughly. And then once we have all of that machinery, we can actually take a gradient step. And now I'm showing what happens if you repeat that instruction 10 times. You just sort of shift the little x from its original value a little distance. Or I could do it 150 times. And then now we'll see gradient descent take the traces much, much closer to the most probable value for the peak of the distribution. But there's lots of other inference algorithms that show up in probabilistic modeling and inference other than gradient descent. So for example, I might use a Metropolis Hastings algorithm to start making updates to individual variables. So here's an inference program that says 100 times use this tactic called resimulation Metropolis Hastings on a minimal subproblem that's chosen at random by picking a single latent variable now and updating it. And so that generates this little random walk where the x only moves either horizontally or vertically on each step. So this is another type of approximate inference algorithm that is actually surprisingly common in computational statistics. And we can also write inference metaprograms that explore multiple traces at once. So now we're going to explore 10 traces at once using gradient descent. So you can see they start out kind of spread out and then coalesce to near the center of the probability distribution. Or here we could, and then we could maybe do a bunch of steps of that Metropolis Hastings algorithm before. So now you can see sort of a cloud of executions following the target distribution. And we could do the same thing with 100 particles. So now we've got 100 executions that are resampled, reset to the prior, then we're going to do 150 steps of gradient descent. So you can just imagine this cloud of executions starting at random and coalescing to the high probability regions. And then after that, we could do some Metropolis Hastings to adjust each one. And we can see we've got a pretty faithful representation of the true target distribution on executions. So this is the conceptual model for inference metaprogramming. And if you learn a model like this, it gives you a way of translating what's going on in papers and conferences like NIPS and ICML and UAI, and also in some computer vision and robotics and data science code bases, where some core part of the application is defining a model and then giving an inference algorithm that does operations like the ones I've described here to approximately explore the space of settings of the variables in the model, which in the case of probabilistic programming means explore the space of possible executions of the model code to try to find likely executions. And Venture, which is a research prototype we made to explore this idea, has a whole bunch of inference metaprogramming operations that give you a nice basis set for a broad class of inference algorithms that are used in practice. you can see implementation details in the tech report, but it supports, gradient-based optimization via automatic differentiation, MCMC and sequential Monte Carlo, variational inference, and more advanced Monte Carlo techniques. I won't go into the details here. Okay, so now we've seen an extension to this probabilistic programming paradigm where we're not just representing a model as code, but we're also representing an inference algorithm. It's a kind of metaprogram. It's a non-standard metaprogram because it's exploring alternate behaviors for the input metaprogram. But it's a metaprogram. That's another type of code. So we're now here. So let's take a look at an application to machine perception. So there's a very old idea in computer vision which says that the problem of 3D machine perception, which is it can be viewed as the problem of going from an image to a scene description, where if that scene description is kind of like what you would feed into a renderer, such that you would reproduce the original image. This idea is sloganized as sometimes called the proposal of it for analysis by synthesis, or vision as inverse graphics. And it's actually at the root of very old proposals for understanding human 3D perception, as well as engineering better machine perception systems. So here's an example result from a probabilistic programming system we built to explore inference metaprogramming in the context of this problem. So the application says, I've got an input image of a face. It might be face on, or it might be slightly rotated. And the task I want the system to solve is tell me what the face would look like if I rotated it to the side or lit it differently. Imagine the face under some different circumstance. And the way the system does it is it infers a 3D model which can reconstruct the input and then applies ordinary graphics operations to that 3D model. And you can read about this in a paper that was in CVPR in 2015. So the way that this works, from a probabilistic programming standpoint, is we write a probabilistic program which generates scenes, renders them, and then kind of compares them very roughly to the input image. And then we're going to write an inference metaprogram that works backwards from an image to try to find the probable scene. So the scene generator in this case of faces is some code that uses off-the-shelf graphic libraries to generate random meshes, texture maps, and camera coordinates and lighting positions. And it's such that once you render them, you get a face. And if you ran it a whole bunch of times, you just get a whole bunch of synthetic data of faces. And the inference metaprogram that we use uses a combination of gradient search, like I showed you before, a slightly different family of Monte Carlo techniques, slice sampling instead of Metropolis Hastings, and bottom-up proposals that are trained using that synthetic executions of the probabilistic program. And it's a combination of those operations that gives us good performance on our benchmarks. And it takes about a page of code in picture to write all that, and I won't go into the details here. But here's an execution. So on the left we're showing the data, and on the right we're showing the sequence of reconstructions that the inference metaprogram walks through. So analogous to the sequence of locations those little X's walked through earlier. So initially the reconstruction really doesn't look much like the face, but then it starts to kind of get fine-tuned. And initially the changes are big, they get smaller over time. So the big initial changes are the bottom-up proposals kicking in, where some pattern recognition system's basically trying to roughly match the image to some synthetic face. And then after that, the gradient search and the Monte Carlo technique are kind of fine-tuning the model to match smaller features. And you can also use this to solve problems like inferring models of the 3D pose of a person from real images. Now, a key technique we use in this kind of inference metaprogramming, this will help to connect probabilistic programming with deep learning, is we use bottom-up proposals that are trained on synthetic data generated from the probabilistic program. So that probabilistic program for human body poses I showed earlier, we can use to generate lots of different images of bodies along with their true pose. So that means we can generate as much labeled data as we want to apply machine learning techniques to give us rough algorithms for approximately solving the inference problem. And this approach gives a bridge between probabilistic programming and modern deep learning that a bunch of researchers have been exploring, including our own group. So I say this here that I think, over the next several years, we're going to start to see a larger fraction of modern deep learning techniques, especially those that are based predominantly on synthetic data, reinterpreted as a kind of probabilistic programming, maybe along the lines of what I showed. And this approach allows us to combine deep learning techniques with Monte Carlo techniques and optimization techniques in a way that the standard pipelines don't make very easy. For example, my lab has been working on a system called GEN. This is principally work by my PhD student Marco Cusimano-Towner. There's a talk that should already be online on GEN from the 2018 Probabilistic Programming Conference for people who are interested. But GEN, I'm really excited about it. It's one of the first probabilistic programming languages I actually want to use. And GEN is designed to make it possible to combine modeling and inference techniques from multiple paradigms. So deep learning, graphics engines and physics engines, graphical models, Monte Carlo inference, deep inference networks, and optimization. It supports programmable inference, like I showed, in all the ways I showed, so use algorithm X to update, or use some algorithm to update X given Y, but also custom proposals and algorithms, automating, deriving things like proposal densities and Jacobians. Unlike Venture, GEN is designed to be fast enough for real-time applications. So its out-of-the-box performance appears to be competitive with handwritten samplers, of course worse, but competitive. But the architecture is designed so that users can optimize slow components in place without having to change the testing code that they wrote. So we think it's actually got a reasonable design for letting you rapidly prototype something and then optimize it in place for deployment. We've started to do some experiments with a couple of different compilers, including a JIT compiler, a simple interpreter, more aggressive compiler based on more static analysis, and we're starting to see the kind of performance trade-offs that one would expect from that. Okay, so we now talk a little bit about probabilistic programs that learn the structure and parameters of probabilistic programs from data. Actually, let me pause for a second, because I have a little bit of time. Are there any questions so far? I know it's late in the day, and this is probably a little bit different in theme than many of the talks here. Yeah?
This is potentially impossible, but it seems by combining different inference techniques, it seems pretty easy to write like a sampler that kind of feels right, but is wrong. Is there any kind of way to prevent people from accidentally doing that?
Yeah, great question. Now that we have inference metaprogramming, I think tooling for inspection, testing, debugging, and verification is a really important next research area. We've, of course, been jury-rigging our own such tools over the last years of work building these platforms, but I think there's a lot of low-hanging fruit there. Yeah?
Is there a notion of online-ness with probabilistic programs? Because it seems like there's a lot of kind of offline tuning of the trace, but there's also a lot of kind of research going into RL these days. So
yeah.
How's that kind of work?
Well, I guess let me answer that. Let me say this and see if that connects. So one sense of online you could mean is online inference. Okay, so by online inference, I mean, let's say you're doing an autonomous driving application. And you're building a perception system that's going to get a stream of video, and it's got to produce a stream of scene interpretations. So at least in principle, there are probabilistic programming languages that would let you prototype something like that. We designed GEN, for example, because we actually want to take those applications seriously. over the next few years. So that sense of online inference, definitely. Now there's another thing you referred to, you mentioned reinforcement learning. So are you familiar with the training system for Dactyl from OpenAI? So Dactyl is a controller for a robotic hand that was trained using a kind of weakly synchronized-ish gradient descent on heavily domain randomized training data from a whole bunch of physics simulators. Right, so they had this whole cloud setup which ran a whole bunch of simulations and then added a whole bunch of noise to them and then did gradient descent to sort of tune the perception system and the URL system. And so there's that sense of online training, right? And in principle, that's applicable to the compilers for probabilistic programs. That might sound funny, but by compiler, right, I mean this act of training an inference algorithm offline, but that can be done by an online algorithm. Right, so like in picture, you could imagine having, the proposal that's roughly going to initialize the face trained in an online fashion. But from the standpoint of the probabilistic programming application, that would be like an online compiler that you're using offline, probably, right? Because before you ship the application, you would run it, but maybe you could run it. So I hope that wasn't too confusing, but I think I said that correctly.
Yeah, I think I got all that. That makes sense.
Okay, great. So this approach, right? So this idea of inference metaprogramming can be applied to application areas for probabilistic programming that are relatively mature, and ones that are newer, like this inverse graphics stuff. But I think over the next few years, we're going to see machines, not just data science applications, but also robotics applications becoming increasingly practical with probabilistic programming. And of course, I should say that this whole line of research was developed not just for engineering motivations, but also as a tool for exploring fundamental ideas about cognitive architecture and AI. So I think there's going to be a lot of opportunity there over the next few years. Okay, yeah.
Yeah, I just really briefly, could you talk a bit about the implementation of Gen, like is the host language?
Oh, sure. Gen is implemented by embedding in Julia, which is probably what made it cost-effective and time-effective for us to explore a couple of different compilers.
And is it a library? Is it a language extension?
Yeah, I won't say too much more about Gen now. I will defer to Marco's talk just for reasons of time.
Sure.
But if you're interested in Gen, please look at that talk and please write us because we're in the early stages of turning Gen into a proper open source project and actually taking it more seriously as an engineering vehicle.
Thanks.
Yeah. Okay. So now let's look at applications where we have data but no probabilistic program. So to get started, we need to somehow learn the parameters and structure of the probabilistic program first. So the pedagogical example I'm going to use is re-implementing a system called the automatic statistician, which takes curves like this and extrapolates them. So let's take these two. So this curve, what do you guys think? How do you guys think this curve continues? This, yeah, okay. And how about this one? Right. So some people actually just went like this, and other people added the periodic overlay. Okay. So both those predictions, those intuitive predictions, are borne out by the real data. So the top-level source code for re-implementation of this looks as follows in Venture. So you assume that there's source code for some probabilistic program, which is generated at random by another probabilistic program. And then you produce an executable from that source code. And then you load up your XY data, and you observe that running the executable on this vector of X inputs produces the desired Y outputs. I'm going to say a little bit about what the language is that makes this work. We have a paper conditionally accepted to Popple this year that's based on stuff that's been in tech reports for a little while. It kind of formalizes all of this and gives sufficient conditions for sound synthesis of these programs and all that kind of stuff. But here's the inference metaprogram. Or here's an inference metaprogram, I should say. There are many you could right, but this inference metaprogram uses block gradient descent on all the hyperparameters, and then Metropolis Hastings algorithm on the structural random choices in the program elements. So we're using gradient descent for the parameters and a kind of Monte Carlo technique for exploring the structure. And the kind of results you get shown here. So here's the airline passenger data, and here I'm showing sampled extrapolations. So the data in black was given to the program, the data in red is test data, and here are two kind of extrapolated cycles. Here's an interpolation example. So you can see that over here, there's missing data where there's a periodic structure. And over here, there's missing data where there's just kind of some smooth filling in that's kind of qualitatively different in those two different regimes. So in fact, it turns out that this kind of extrapolation and interpolation can be quantitatively much more accurate than many standard systems for time series forecasting that are out there, including Facebook's profit system. I mean, on our benchmark so far, right? And ARIMA models and other sort of standard econometric techniques. Yeah.
How constrained is the code generation?
Yeah, I'll show you in a minute. That's a great question. The next slide will give you a little bit more sense of that. So, so the key to making this work is that we're doing synthesis over a domain-specific language of models that somehow trades off the ability to explain any time series, at least in principle, albeit perhaps with quite a complex program, with the ability to describe very simple, important kinds of structural motifs in time series very concisely. So there's a high-level DSL, which you can embed in S expressions. It looks something like this. Squared exponential just means, well, okay. How many of you have seen Gaussian processes? Okay, so so I'll start with this example. So this example says there's a change point, which means that to one side of the change point, there's one behavior, and to the other side, there's another behavior. And so there I'm showing the DSL, and here I'm showing sampled executions of the probabilistic program. And here I'm showing the embedding of the DSL, basically by compiling it into Venture. So what the DSL expressions do is they define this structured object called a kernel for a Gaussian process. And that's the form of this code, right? So it's highly constrained. Highly constrained. But from a modeling standpoint, it's also highly expressive. So relative to model classes that people deploy in practice, it's much more expressive than many. But relative to all possible venture programs, it's sort of unimaginably restrictive. But I'm actually quite happy with this DSL and some others as examples of a good kind of engineering trade-off to be striking, which is another opportunity for the programming languages community to really help data science. Right, which is, how can we formalize example DSLs and the principles of DSL design for this kind of DSL? Right, which is a language for some domain-specific family of models that will at least initially be produced by a synthesis algorithm from data, and then maybe fine-tuned by a person or overridden in parts, because of course once you have this code, you can say, throw out this part, add in my own knowledge over here, etc. Which is sort of important from an explainability standpoint, and also just practically because we might not expect a synthesis system to do as well as a person could, given all the knowledge that a person could bring to bear. Okay. So here's a probabilistic code that generates abstract syntax trees for the DSL I just showed. And the basic structure is a recursion. It's like a probabilistic context-free grammar that just essentially runs the grammar for the DSL forwards driven by random inputs. The only one interesting note is that it tags choices with whether they're structural choices or parameters, so that you can refer to them when you're writing your inference metaprogram later on, and say things like do gradient descent on the parameters, but do a Monte Carlo search technique over the structural choices. And it's that factorization of code for modeling from code for inference that drives the lines of code compression we see relative to baseline implementations. So it turns out in this case, it's about 70 lines of code to write this structuring, this time series structure discovery technique as a probabilistic program, versus about 4,000 lines for the original system. And just to give a sense of the library, the weight of the libraries, the entire Venture Inference Engine and the Gaussian Process Library are each about 2,000 lines. And the Gaussian Process Library for, and so the automatic statistician system, which is abbreviated ABCD, that just happens to be the acronym that got popular in machine learning for automatic Bayesian covariance discovery. They're using a much more full-featured Gaussian Process Library that happens to be 14,000 lines of code. And I think personally that this type of DSL will be increasingly practical over the next few years. So let me just give one other example, which is sort of more of a real-world application that my lab's been pursuing largely through, actually both through projects with DARPA and projects on campus at MIT. So the use case is automatic data modeling for science. So here, this is all in the context of the BaseDB system, where instead of time series data, we're starting with databases. But BaseDB lets you synthesize probabilistic programs given both qualitative constraints on those programs, like you can insist that a variable must predict another variable, or you must have some dependency, and quantitative constraints, like you can say, I want to insist that there is some factor analysis that governs the relationship between some variables. You go from data and qualitative constraints and quantitative assumptions to probabilistic programs, and then there's a probabilistic programming system that takes a query and the probabilistic programs representing models and produces answers. That's the architecture of the system. But what we're using it for is to go from lab experiments, which produce experimental data that you can think of as being messy spreadsheets, to probabilistic programs that you can think of as virtual experiment simulators. So they're an attempt to model the data generating process and the data capture process by which the spreadsheet was produced. And then we can pose various questions of scientific interest as inference problems on these probabilistic programs, or in some cases, program analyses of these probabilistic programs. So here's just a very simple visualization from an application in synthetic biology where there was a data table that had 300 rows. So it's very sparse data by the standards of machine learning. Not a lot of replicants. And here, I'm just trying to give you a qualitative sense of the accuracy of synthesis. So I'm projecting the data down onto two pairs of variables, which we know from our understanding of the biology and the experiment design should predict one another. And I'm showing the real experimental data in red and the virtual data from the probabilistic simulator in blue. So you can kind of see that qualitatively in both cases they agree, but I think it's important that they agree even in cases like this, where there's kind of these funny sparse patterns of noise or other bits of texture that, if you just did a regression model, for example, you would miss. And one of the features of the BaseDB platform, which we do this work in, is that you can query these probabilistic programs using a SQL-like language. So you can say, simulate CYSM and YBit from data, and you can compare that to selecting CYSM and YBit. And that gives a way of teaching people who understand the vocabulary of databases. It gives them a way of teaching them how to think about model criticism. They can at least say, okay, well, maybe I don't know the statistics, but I can understand qualitatively the idea of comparing my real data with virtual data using language constructs that are similar to the originals. And BaseDB lets you say things like simulate x and y given that x equals 3, right? Or under various constraints. Okay. So There are a bunch of use cases of this kind of thing in practice. I mean, these are related actually to some of the commercial use cases of BaseDB that we've seen over the years. So one of the most important are just screening data for ETL and lab protocol execution errors. I think there are going to be versions of this that will show up in data engineering pipelines as well, outside of science. There's detecting drift between old and new batches of data, detecting multivariate relationships among variables, and estimating how variable you expect the outcome to be for some experimental condition. And these are, of course, all applications that you can try with fully automatically synthesized probabilistic programs, but you may be able to improve performance by customizing the probabilistic programs after the fact. And we've done that a little bit in research papers, but not too much yet in real-world applications. Okay, so just to recap, in this talk, we've seen the standard model of probabilistic programming, where we're using code to represent probabilistic models, which I've tried to argue lets us broaden the scope of AI applications. We've seen that we can make inference programmable by using inference metaprogramming constructs that explore the spaces of executions of code in particular ways, and that can be applied and combined with deep learning to get a new interesting approach to problems in machine perception. And we've seen that we can take problems where the data is very sparse or there's lots of structured domain knowledge and learn probabilistic programs from data by synthesizing probabilistic programs that fall within a domain-specific language. And I at least gave you a pointer to an application of that in automatic data modeling for science. Okay, I have a couple more minutes for questions. Any questions? Yeah.
I was sort of wondering, in the faces reconstruction, was that data that you were working over features of faces that were then, or were they like cuts?
It's actually pixel images. So for the faces, our probabilistic program was sufficiently photorealistic that you can just apply it to images. But in other cases, we might, like the human body pose example, we were projecting the renderings and the real images into the feature space of a convnet trained on generic real images. So that whole area of designing those comparisons is one we're actively looking at using Gen. Maybe I'll just say one other thing that might stimulate more questions. Sorry, you had a question?
I did have a question,
Yeah.
actually. Can you imagine a reality where probabilistic programs work with deterministic ones? And I guess, if so, then why? If not, then like, what really breaks that model?
That's interesting. Well, let me answer like so. So certainly all existing probabilistic programs are embedded in a metaprogramming ecology that is all traditional software, right? So at that level, of course, they only exist because they live within that ecosystem today. And I will say that we're designing the Metaprob language, which is the language we're using for the next version of BaseDB. So Metaprob is embedded in Clojure as a lightweight library, and I'll say a little bit more about that. But we formed the seed of the open source engineering team over the past year, and we're just sort of starting to grow that effort. So Metaprob is being designed specifically to help make probabilistic programming easier to embed, both in the browser via the ClojureScript compiler, and in enterprise IT environments via Clojure running on the JVM. So I think there's lots of interesting applications where we'll see tight interplay, basically, between database backends and probabilistic programs. You could imagine something that screens data coming into or out of data lakes for probable errors, right? Or interactive data analysis tools in the browser, where the probabilistic code produces executions that you can then edit in the browser yourself. So those are two examples of systems where you might see tight interplay. I think you'll see a different type of integration in robotics, where you might imagine modules in something like ROS that take as output the sampled scenes from a machine perception system written in a language like Gen. So those are just two examples of how we imagine probabilistic programming integrated. last question.
Just to make sure I understand the notion of inference metaprogramming, I want to contrast it a little bit with like, you are contrasting with other probabilistic programming languages.
Yes.
And as a contrast that, there you just say, do MCMC, but here you have finer grained control over the like specific parts. You know, you can sort of like constructively build inference from subparts, or is it that you have to also modify the original model to insert these like, you know, pound latent data or kind of?
Yeah, so that's right. So yes to all of that and more, right? So, you know, traditional probabilistic programming systems typically have black box monolithic inference engines. Inference metaprogramming lets you do which is quite out of sync with best practice in many areas where modeling and inference is applied. Applying inference tactics to subproblems, which requires naming subproblems and defining them, that's a part of the puzzle, but actually one needs much more than that, including the ability to specify custom inference algorithms and user space code, and interleave those with standard inference libraries, and all kinds of stuff like that. And so Venture takes a certain step in that direction, and then Metaprob and Gen both go a bit farther.
Thanks.
Yeah. Okay, thank you very much.